right now, the virtuous cycle that we're working on is what we call the virtuous cycle of autonomy. Here, with most virtuous cycles, you start off with this idea of customer demand. Either it begins organically with users perhaps wanting some piece of software, or it's already happening. Like, hey, right now, you live your life with the idea of a smartphone, and you that's a innate demand almost at this point in time, right? Because customers have a demand for some product, that means they're using it and they would like to ultimately get new features and new uses out of that product or whatever it is that they're demanding. And that leads to the development of new types of hardware. In particular, what my group is interested in is this new surge in sensors and accelerators. So at the end of Moore's law, when we talk about new hardware, we're not talking about the number of transistors on chips doubling, but we're really talking about a very targeted delivery of those transistors on chips to speed up very specific workloads. The other thing that we're seeing a lot of are just really reduced costs on the hardware for sensors, right? You would be surprised if you looked at the trend for what it takes to create the filters that ultimately power your cameras. Those have been declining in cost. The silicon associated with those have been declining in cost for several years and suggests that they will continue to do so. So you have these two things that sort of seem to make sense, and that leads to new software development, right? So I have these tools that I'm already using, like smartphones, laptops, cloud computing. And now I have on top of that new sensors, new accelerators that have the potential to give additional power. But the specific type of hardware that I'm talking about here are really interesting because sensors in particular really enable a wide range of use cases. So we can talk about something as simple as a pulse monitor, right? I could use that sensor to understand if I'm having a heart attack. I can use that same sensor to track my fitness level. I can use that same sensor for a myriad of other reasons. And you can see that with the addition of sensors, the potential use cases, that is, the things that the customers are actually going to demand, can really blow up and easily overwhelm users. And this leads us to the first catch to what we call this virtuous cycle of autonomy, which is that we really want fully autonomous, data-driven systems that are going to use these sensors and actuators that are now available to execute complex tasks without human guidance. Here, the italics are on the phrase without human guidance, because if all of these potential use cases require a human to intervene, to make decisions, to ultimately power the app as we've historically thought about it, humans would just be overwhelmed. It's not really an option. So here I'm showing you what we mean by autonomous and data-driven. This is a choppy video of my student in Dries Labs. He is playing around with one of our autonomous drones. So this drone's been programmed to avoid human beings. So it's taking a picture where it's at, and if there's a human in front of it, it's trying to run away by just going to the right. That's hard-coded in this example. At the end, you see he sort of allows it to take a picture of something that's like his chest, so it doesn't think there's a human face there, and it decides to land safely, right? So what do we want? We want these devices, these new cool sensors and technologies that are available, and one of those would undoubtedly be unmanned aerial vehicles, to be able to autonomously perform these types of tasks without a human using a remote control and telling imperatively exactly what the drone should do. So this part is really cool. If you think about it from our virtuous cycle of autonomy, you can see you're going to have these potential use cases. And as you develop out these potential use cases, you end up building very complex toolkits. So I'm highlighting with the mouse. It only took Zichin about 2 weeks to build this app. And this was a few years ago that he built this. But at the time, look at all of the different software platforms that were involved in order to create what probably, or hopefully to you, seemed like a ridiculously simple autonomous routine. So what happens is you have all of these complex software platforms, and you're going to end up trying to simplify it, right? You're going to try to turn this into something that is Python friendly, something that can be run with a couple of command lines and eventually abstracted. So that creates a need for what? Myself, yourself, folks that are really good at coding and taking computer software and turning it into something that is easily usable by the masses. But there's a downside to it. Every time we have a system that has this many components inside of it, we run a risk. Each one of those components gets some number of instructions slotted to it, and often those instructions aren't needed. They're redundant, they're bloat. And so we end up having slowdown, right? So this software bloat slowdown. Now, in a traditional virtuous cycle, for instance, the one from James Laris, after you have slowdown, the way when we had Moore's law, the answer was just wait 2 years. You're going to have 2x more transistors. Life is good. We don't have that anymore. So now we really need to think about how we're going to do resource management for software that looks like this. And that resource management has to be so good that customers get the potential use cases that they want, and they still feel like the tools, the devices are useful to them. So taking a very, very high level view, we view the solution to resource management as being an edge computing problem. That is, we know that on the devices, the sensors or the actuators themselves, we're going to have not too powerful processors, but if we have data that's generated there and processed there, we have very fast latency. If we are willing to send a network message, we can reach something faster. We can go to what we typically use, the term is gateway, where we have maybe a laptop, maybe a couple of servers that are just one hop away with a network message. And now we've got more powerful processors, but that network message costs us in terms of latency, right? And we can keep playing this game until we get to the cloud, and that's where the buck stops, because there we have unlimited throughput, and whatever our latency is to get to the cloud is whatever our latency is to get to the cloud. So what we would really like to do is find the sweet spot here for each of these applications so that we can map those platforms that I described before onto individual nodes or individual components of the edge computing landscape to figure out where things should run for maximum efficiency. And if we do that, it is our belief that we can have really efficient resource management that continues to satisfy customer demand for these use cases. So that's a high level view of the virtuous cycle that we're going for. Now let me introduce a very concrete but fundamental problem that arises with data-driven systems. So you can see this loop, right? Because the systems are driven by data, that is, they're autonomous, you have this inner loop. That is, you're sensing something, you're trying to figure out what you should do based on what you've sensed, and then you take an action. And that action may lead to something that users can observe, right? And ultimately leads to a transaction like a normal computer system. But it also has this feedback loop. The action that I just took is going to affect what I'm able to sense next if I'm in a continuously running system. And this inner loop has complications associated with it. The action that I take affects what I sense. What I sense affects the compute that I perform. And so now the compute that I perform may actually be influenced by actions that I've taken prior. And you can have these ripple effects where it's really hard to know how much hardware do I need to provision to a particular node. You can imagine in our previous example with the autonomous system, the amount of compute, if the drone flies to the right and there's no human there, is very low. But if the drone has the ability to fly to, I'm sorry, if the drone flies up and there's nothing there, it's very low. You just land and it's great. But if I have humans lined up all to the right, I may actually need to repeat this compute process many times before I can find a safe place to land. So how would we go about modeling the amount of compute resources that we need for one of these data-driven systems that has this feedback loop inside of it? For this, again, I said if the rapture came, I'd be a systems person. So this is my systems-centric history of performance modeling. But ultimately, I'm a performance modeler. So please bear with me that I may be missing some domains contributions, but I do believe this captures the state of performance modeling for computer resource management in the past. You go way back when we're first building computer systems that can be used by people in the masses. You're talking about transactional systems that are really managed by ad hoc policies because they're just not widespread enough and the need to scale them wasn't there. Around when I was getting my PhD, one of my big contributions was to help the community shift to a concept that I refer to as model-driven management, which is where you take a hard look at the software that you're running, and you try to develop some sort of an analytic model that predicts its behaviors. And once you have that analytic model, you can say, great, then I sort of know how this is going to perform in a number of different conditions, and I can search for good policies to decide how many resources to provision. Immediately following that was, of course, to replace the idea of learning about the system yourself and to use machine learning, right, which has totally transformed the space. And here you just think of things as a function. And if I have enough training data, I'm going to map workloads to optimal policies, and I'm just going to learn that function. And so the case that I'm making to you today, again, at a very high level, but you'll see a couple of examples on this, is that we should move to a new era that is data-driven management. Data-driven management means that we're going to consider the execution environment and that we're going to integrate that execution environment into our models for how to provision resources. So it's no longer just a function of the software and the hardware, but we really need to know something about where things are executing and what they're sensing in order to decide how many resources we need. Hopefully, at this stage, that's not too controversial of an opinion. But let's go into some technical details and we'll talk. I'm sure there will be more questions and controversy. Are there any questions at this stage?
Any questions?
By the way, totally feel free to interrupt me at any point in time if you have questions. We'll get into technical details here, so folks will undoubtedly want to ask more. How am I doing on time?
Sure.
Great. So I'm going to talk about this with examples in two use case scenarios. One is what we've been doing in precision agriculture with modeling and managing fully autonomous aerial systems, like the example I showed before. And the other is in data-driven management in the cloud computing domain. Precision agriculture. Right now, if you're doing agriculture, there's this new sensor or accelerator that really matters to the field. It's the unmanned aerial system, so also known as drones. What a drone can do is today's drones can take off, land, hover. They can fly to preset waypoints and perform defined aerial acrobatics without a human in the cockpit. And that means that they can take on missions that are more dangerous, like going into fireplaces, that require perhaps traveling at lower levels that would be dangerous for a human to fly at because of the risk of crash. And importantly, that are just not at the same price point economically, right? So here I have this picture of a drone doing photography for a wedding, right? You wouldn't want to pay a pilot to fly over your wedding party just to take a picture. But, you know, maybe I'm willing to pay $150 to have a drone do that. So that's an unmanned aerial system, which many of you are familiar with. Today, those are piloted by human beings using remote controls. When we talk about a fully autonomous aerial system, we're talking about those drones being piloted wholly by software. And so here's the workflow for your traditional UAS, right? You have some mission goals. The operator defines the flight path, either with a remote control or setting some GPS coordinates. The drone goes out and does a flight, senses the data that you want to sense, and gives you that data. And now the operator decides, did I meet my goals or did I not meet my goals? With fully autonomous aerial systems, again, I'm just motivating exactly the types of systems that we're concerned about. Everything is done with software. So everywhere where you're seeing operator above, replace that with software below. You have some pathfinding software, and then that's going to define the waypoints that you fly to. You'll still do the same unmanned flight and sensing of data. But then after you've sensed the data, you actually are going to use software itself to do the analysis to decide if you continue flying, if your goals are met, or if your goals are not met. Again, a very simple example of this can be Zichen's autonomous drone that we saw in the earlier slide. So why do we care about FAAS in agriculture? So the potential for AI in agriculture is really, really high. Right now, we're losing about 50% of our crops due to crop disease, weather, whatever it may be. So these things, if we are able to detect them early enough, we can take preventative and preemptive measures to condition the field to make it robust to problems. But the problem is going out and flying over a field on a frequent basis just to detect a particular problem on a corn stalk is really expensive. Because remember, individual corn stalks are quite cheap. Think about what it costs you to go to the grocery store and buy corn. But somehow collectively is where we gain all of the value from those. So it's really expensive if you wanted to do this with an airplane weekly flying over. It's about 35% of what would be your farm profits if you were operating a farm here in Ohio. Even if I used a UAV, if I'm still paying a human being with the expertise to pilot these things with a remote control, like myself in this photo, you're still talking about consuming almost 15% of farm profits. So here's what the state of the practice looks like if I am using one of these ARP operators to fly over the field. Because remember, an operator is going to go out, collect as much data as they can, and ultimately try to make some analysis based on that. So the de facto is what's called lawnmower missions. And that means the drone starts off at some place. Oops. Animation got messed up there. Not maybe. Hands off. Will you? Okay. Not sure what happened there. So what the drone is going to do is it's going to visit each one of these GPS waypoints. So we'll call a GPS waypoint the center of one of these images. And this is from a real field that we explore in Ohio. And as I get to the center of each image, I'm going to take the picture, and eventually I'm going to give this whole map back to the pilot. And I'm going to ask the pilot, perhaps find the region that is most representative of this field. The pilot decides that it's the center point, and then you're done. But in order to do this, I had to visit all 9 GPS points. FAAS not only allows you to remove the cost of the pilot, but it also allows you to do this much faster. Because now, when we do the software analysis to decide if our mission is done, we can employ reinforcement learning. And so the way that that may work is that if I start at this location, I may look at this image and realize, hey, look, there's a street in the middle of this image. This isn't going to lead me to the most representative image for my field. Maybe I'll fly up instead of to the right. And I can see the same thing with figure B, right? So again, I run into the street, so maybe I'm going to avoid this intersection. I'm going to fly to the right. And now I've got another image that looks like, great, I visited a GPS waypoint that doesn't have anything other than the crop inside of it. This may be a really representative image, and it may be okay for me to just stop here. That is, the utility of this image may suffice. So this is the basic idea for fully autonomous aerial systems, right? So what we're doing is we're getting a benefit by using software to replace even expensive UAV operators, and we're using software to reduce the amount of time that we have to spend in the air. Now you can see from this a real problem, which is depending on the algorithms that I'm using for the software analysis, my flight pattern is going to change. And that environmental factor ultimately is going to affect the amount of compute that I need to do. So here we're considering just two algorithms. KNN, in this case, is looking at, for each image, it's finding the 3 images that are most similar to that image. And it's going to tell the drone to take the action that was most common amongst those 3 images that were available, up, down, left, or right. Okay, I'm sorry. I think K was larger than 3 in our exact experiments, but I don't know the actual number K. A star search, for those that know from AI1, builds a map, right? So I'm going to take this image, and then I'm going to hypothesize about, from other images I've seen and from the image that I just have, about what may await in the future. And so I'm basically recursively running this KNN search to create a map of the field and then taking the path that is best defined by the map. So A-star search tends to be more efficient than KNN, though not always. So what we can see in this example is that the A-star search is what I just showed you. Hey, I visit 3 places, done. The KNN search is much less efficient, right? If I look at, if I just use KNN, I may take a totally different path to eventually get to the waypoint that I'm interested in. So the compute demands for choosing between these 2 approaches are not the same. And what we're really interested in is, how do I model that? How do I know, how many compute resources I'm going to need when I go out to map a field. So what we've created is this idea of an autonomy cube. And the autonomy cube is our way, recall with data-driven management, what we're trying to do is to understand the environment. The autonomy cube is our way of characterizing the environment for precision agriculture, for a crop field. And basically, it's a descendant of the data cube by Jim Gray. The data cube allows you to compute any possible group by on top of your data, group by or pivot on top of your data, and it returns that result. The autonomy cube allows us to simulate any mission that would be executed on a particular field. So you can think about it as a cube of all of the images that you could collect from a particular field. In the case of precision agriculture, since our field doesn't change too much, you can really think about this as a full 2D capture map of the whole field, something like what you would get from the lawnmower exercise. However, instead of deploying that in practice and getting a 2D field for everything, what we're going to do is use a representative sample of autonomy cubes offline to create a model that allows us to learn the effects of different software and different hardware on the paths that we take. So we're going to use those autonomy cubes basically as an offline profile of the environment to ultimately drive data-driven management. So I'm not, for the sake of time, and I wasn't planning to at the start, going to go into exactly how we build the model. I encourage you to check out our symposium on edge computing paper. There's really cool stuff on modeling the energy consumption of drones, et cetera, inside of there. Instead, I'm going to talk a little bit about why the autonomy cube is so very important and how we ultimately used it to improve management for precision agriculture. So here I'm just showing you the exact same example that I showed you before. Let's say that I didn't have an autonomy cube. Let's say that instead of having a representative sample of autonomy cubes, I had a representative trace of flights that I had flown in the past, just missions that I flew in the past. And those missions were based on software configured using the KNN algorithm for our reinforcement learning. If I had later changed to move to the A-star algorithm, think about how that A-star algorithm would have to, how we would try to predict the compute requirements for the A-star algorithm. Well, the A-star algorithm, recall, it immediately told us to fly up from A1 to B1. But we don't actually, for this trace, have A1 or B1 in, I'm sorry, we don't have B1 in our data because that wasn't a part of our mission in the prior mission. So we have to try to infer compute using the data that we have, which is A2. So we try to use A2 and then we would say fly to B2. We don't have that either. So then we say, well, we do have A3. So we fly to A3. By the time, ultimately, we're assuming the compute costs for A-star mimic the compute costs for KNN, but we're ignoring the changes that are happening because of the actions that we're taking. So these ripple effects are being missed. So what does the autonomy cube provide here? Here we get to literally know the entire field. So no matter what we change our software to, whether it's A-star or some energy aware particular algorithm, we can predict what the compute needs will be even with the ripple effects involved. How much does it matter? Well, you can see in this example, it can be pretty significant. Depending on the changes that I make in terms of architecture and software, a small change maybe you're talking about a 1x to 2x difference in terms of the normalized error in terms of mission throughput. A big change can be an order of magnitude higher. So we went about evaluating our approach to do this type of management, and we looked across a number of different computer architecture factors and software factors. So the red here represents different software factors, and the black represents hardware factors. I'm just going to highlight hardware because there's some interesting insights that can be conveyed pretty quickly here. And you can see now we can build a model that always corresponds pretty well with what we're observing in terms of the number of missions that we can complete on one battery charge. So we call missions per charge is our throughput measure here. And you can see that the black bar corresponds pretty nicely with the white bar. If we pay attention to the axes here and how it corresponds, you can see that there's sort of this sweet spot, right? It's almost like a curve. So if we are using GPUs in this particular example, we tend to see the GPUs, because of their power constraints, drop our throughput just quite a bit, actually, because GPUs are pretty power intensive, and these are running at the gateway side, so we can easily exhaust batteries for laptops and things like that. Similarly, you can begin to see trade-offs associated also with the different types of software and the different types of architectures that you're looking at. How much does this matter, right? So what I'm showing you here is just some very simple analysis. This is what I led off with on the first two, right? So I told you if I just used an airplane to scout a field, it's going to cost about 35% of my farm profits. If I used an unmanned aerial vehicle, I can get it down to 15%. Now, I've introduced to you fully autonomous precision agriculture, or that is using a fully autonomous aerial system to do the scouting. And if I just build that without doing any sort of data management to manage the compute resources efficiently, I get a very slight saving compared to just using the UAV. And the reason is, while I save on labor costs, I'm still spending a lot on the compute costs because I'm misprovisioning resources and my throughput is much lower than it should be. You ultimately need to do fully autonomous aerial systems plus data-driven management to get really good cost reduction for scouting. And this dotted line here is what it would cost to go out one time with an airplane today. And so you can see our weekly cost for scouting is about that of one airplane visit today. We've had really great success taking this type of work, this type of systems work, and showing its impact in the precision agriculture domain. So we were able to take it to one of my favorite forms, autonomic computing, and sort of present the idea there. But subsequently, some of the top journals in agriculture have really been receptive to the opportunities to further lower the costs for delivering precision agriculture using this type of technology. Right. Still going fast, but don't worry, we're going to make time. I'm going to skip questions on that and save them for the end, if you guys don't mind. So next up, I'd like to talk about how data-driven management manifests in the cloud computing space. So here, we still see the same thing, customer demand for cloud computing, especially, and for emerging accelerators like the Google TPU. And we're seeing this increased opportunity for sensors, which when we're in the systems domain, we really call that, well, okay, so things like C groups, things like fine-grained DVFS and power scaling, very fine-grained performance counters, all of these things give us the ability to do what? Virtualization, right? We get to divide up these very powerful or very cool processors and server systems and carve them up specifically for application-specific optimizations, because we have the opportunity to sense at a much finer granularity than we have in the past. And this is driving the field of AI ops, which I have a PhD student that's coming out this year. He was a part of a startup that actually was working in this space, or is working in the space of AI ops. So expected to reach about 4 billion per year in the coming years. So let's talk about one specific problem inside of AI ops, and that's computational sprinting. So computational sprinting says, I have a processor that's running at some de facto speed, but that's not the very fastest it could run. I could actually overclock it. And you could think about multiple ways to overclock processors today. One is to do the traditional thing of kicking the clock rate up, right? If I increase the clock rate, I'm going to burn more power. And as I'm burning more power, I'm draining, I'm running the risk of tripping a circuit breaker in a data center, or burning out a wire on the processor, burning out the power supply on the processor. Alternatively, I could also look at that as a core scaling problem today, right? So in the era of dark silicon, I may have so many cores that some cores are sort of inherently turned off on, or by default turned off on my processor, but they may be accessible for short bursts. And again, here the short burst is going to consume more power, but I can only do it for a short amount of time. So I have a budget. So the basic elements here are, I have this budget, I have some ability to sprint, to use these additional resources until the budget is exhausted. If I'm looking at Amazon burstable instances, I used to get 6 minutes per hour. If I'm looking at power, I may even have something more granular, like I can double the clock rate for no more than, say, a minute. And so I have this mechanism, a budget, and a trigger. Let's talk about this in the concept. Yeah, this is just an example that I'll sort of skip. No, maybe I shouldn't. So the way this plays out is, maybe I have an SLO that says I need to complete some percentage of the queries in a certain number of seconds. And I'm going to define this policy that is, I'm typically going to execute at some default, but I'll time out after a certain amount of time that a particular query has executed, maybe 1.5 seconds if I'm trying to meet a 2-second SLO. And after 1.5 seconds, to make sure I'm going to meet my SLO, I'm going to sprint at 2 gigahertz per second. And that sprint will continue until the query completes, or until my budget is exhausted, right? And if I've got a decent budget, I probably won't exhaust the budget on a particular query. It's just going to run until the query completes. So you can see there are a couple of different scenarios that can play out. I can sprint because a query is running much slower than expected. So the processing time was much longer than I thought, and I ended up reaching the stage where I needed to sprint, and ultimately I had to sprint at the end. Or alternatively, I had to wait a long time before I could start. And so this waiting time sort of adds to the time that I need to make up for. And even though my processing was normal, I still have to sprint just because of the waiting time. So keep these two situations in mind, because they ultimately are the environment that we're talking about. I'm showing you the pipeline for data-driven systems, and here I'm showing you this pipeline for computational sprinting. With computational sprinting, basically I'm sensing query progress and deciding, using the compute to decide, should I sprint or not? And then I set the processor speed, which is also going to affect my budget. If I sprint and a query after me is waiting, that sprint is actually not only helping my current query, it's helping the query that may have spent a lot of time waiting behind me as well. If I sprint and no one's waiting behind me, maybe I'm only benefiting myself. So this environmental factor of the queuing delay really matters in terms of the effectiveness of the sprint. And so at the end of the day, you're observing response time, and you want to make sure that this inner loop is minimizing the overall response time. So how do we do that? Again, I'm not going to go into a lot of the mathematical details here, but I'll highlight, we have this really novel approach that sort of combines first principles modeling and machine learning. So in this case, the first principle models are characterizing things like the sprinting mechanism, which is a hardware specific aspect, and the speed up that we can expect from that mechanism. So if I did core scaling, the mechanism may be doubling the amount of cores. And it's characterizing the software, right? So we're actually profiling the individual components before understanding how their workload varies. The key is once we've gotten those two things characterized, we have this machine learning component that's trying to learn how the environment, the queue length, prior sprints, software phases, and interference between workloads are affecting the actual sprint rate that is being seen. Remember, I may be able to double the clock rate, but if there are a lot of queries behind me in the queue, doubling the clock rate actually speeds things up dramatically and helps me out a lot more than just 2x. So I need to be able to characterize that environment as well. And so we do that using a random forest in one of our works. So if we compare this to, say, a traditional machine learning approach, what I would try to do is just abstract the whole thing with an artificial neural network, right? What you would say, why do I need all of this environment characterization? What if I just learned everything with a machine learning model? And what we can show here is the reason for our approach is that, one, we end up with lower prediction error for much less data, right? So if we wanted to learn the same thing using a neural network, we would have to profile for either a lot longer, or if we profiled at the same rate, we would end up with much greater error in predicting the response time from a particular sprinting policy. Once we can predict the response time for a sprinting policy, we can play the same type of game that we played before with data management, and we can talk about how we compare with other approaches that try to manage computational sprinting. In particular, we compared with one that came from Microsoft, Few Too Many, this approach. And you can see that we were 36, depending on how much speed up you got from sprinting, we could go up to 36% better, 1.3x better than this approach that was actually integrated into products at Microsoft. All right, so now with just with 1 or 2 minutes left, I'm going to summarize and then offer a little bit about future work very quickly. So big picture, if you walk away from this talk, what I'm trying to motivate, what we're really working on in my lab right now is this new type of system that is data-driven, that is autonomous, that is exploiting sensors and accelerators without human input. And these new types of systems, we believe, require a new type of modeling and management in order to decide how many compute resources they require. And so we've talked about two examples. One is autonomy cubes to try to characterize the environment. And the other is developing these models that allow you to use machine learning to infer the environment in addition to some first principles models. But these are just two approaches. Looking forward, you can see that so far my lab has really looked at speed up in the middle ranges, right? So things that go from hours to minutes, like trying to speed up fully autonomous aerial systems, and things that go from seconds to milliseconds, like trying to speed up computational sprinting. On the two opposite ends, I think there's great potential for improvement. I'm going to talk about the bottom end, but I want to highlight actually something I've learned as I've become a more senior faculty member. On the research side, we tend to focus on making things a lot faster, especially in the systems world, right? We focus on those contributions that are milliseconds to microseconds. And I'm sure many of the people on this call, when I sort of throw out this idea for future work, you'll say, oh yeah, I'd like to work on that. But the counter I'd like to highlight is that the things that society needs often are these things that are slower, right? These things that transform processes that take months and transform them to weeks. In particular, lately I've been doing a lot of work on diversity and inclusion and looking at restructuring the systems that we're using at OSU to better find really capable students in our graduate student pipeline, to better assist our undergraduates as they're going through our program. All of these problems are actually not too divorced from data-driven management, but they are on a scale that is months to weeks, and there's really great opportunities there. But I'm not going to talk about that. I'm going to talk about the stuff we all care about as systems folks, milliseconds to microseconds. What can we talk about there? Let's talk about functions as a service, right? So this is a concept that's really popular right now. The idea is cloud computing is too slow. The idea of getting a virtual machine and leasing resources at the virtual machine level, too slow. We really want to virtualize at the level of a function. And so this is an example in Node.js of a simple function that I could deploy on Google Cloud, right? So it's just the hello world, but it's hello world with a function call in between. So in this case, I'm bringing in a HTTP header, and that header includes your name, ideally. And if your name's not inside of it, it just says hello world. But in this case, we want to do something a little bit more complicated than that. Given your name, we're going to have some sort of a lookup table or some process to infer your title. So it's not just going to say hello, Chris Stewart. It's going to say hello, Dr. Stewart or Dr. Stewart. I see a really great opportunity here to improve and to really think about a library that allows you to do functions as a service by characterizing the environment that is visible to the function. So one of the key things with functions as a service is that in order to ensure privacy and security, we don't want these functions to access things like performance counters and low-level system metrics for which they're shared, and we can create some security risks if they begin to access. Instead, we'd like to do an environment characterization. So this import that I'm adding here is this potential environment characterization library. And what that really means is that there's going to be some profiling stage with this function where we're going to characterize the progress of this function while it executes. So we're going to look at the delay that it takes to get to the start of the infer title function, or I'm sorry, to execute the infer title function. We're going to look at the delays to do memory lookup 1, which may be simply loading res into a particular place, memory lookup 2, which may be accessing the data structure body by name, right? And so these will obviously be much faster than infer title. And from these environment delays, what we would like to characterize is which environment delays are symptomatic of potential problems that could arise, problems that could make this function take a lot longer than it normally takes. Then we'll do some principal component analysis and identify when we deploy, the same library is going to deploy with just a couple of hooks automatically inserted in this function to test those delays to see if we should take actions that could possibly speed up the execution. For instance, perhaps truncating the type of inference that we do, sacrificing a little bit of quality to ensure that we meet some operating goals. So that's one way that we could take the data-driven management work and work on it at a smaller scale. It's just one idea. I'm sure many others have other great ideas. I'll take questions after that slide. Thank you all. Thank you all for making the talk. I really appreciate your time. Thank you.